Hello dear students, this is Dr. S.S. Naik from KKWalk College of Engineering. I'll be dealing with Engineering Mathematics 1, in which you will be learning unit number 1, Differential Calculus. In this, you will be learning Rolle's theorem, mean value theorems, Rolle's theorem, and Lagrange's mean value theorems serve as a fundamental theorems concerning derivatives and have very useful applications in applied mathematics as well as engineering. The Rolle's theorem also forms the logical base for Taylor series expansion, which we are going to study after this part. The Rolle's theorem also forms the logical base for the Taylor's theorem. So we'll just see what is Rolle's theorem. The statement says that if a function f of x is continuous in the closed interval AB, that is a less than or equal to x less than or equal to b, and is differentiable in the open interval AB, having the unique derivative f dash of x, and the third condition, if f of a is equal to f of b, then there exists at least one point x is equal to c in the open interval AB such that f dash of c is equal to 0. So here we'll see that the function defined f of x is a continuous function in the closed interval AB, and it is differentiable in the open interval AB, having the derivative f dash of x, and also the ordinates that f of a and f of b are equal, then there exists at least one point x is equal to c in the open interval such that f dash of c is equal to 0. So we are not going to go for the proof of this entire theoretical part, but we'll just see what is the geometrical interpretation of Rolle's theorem. If y is equal to f of x be a continuous curve with endpoints a and b having tangent at every point between a and b, and the ordinates of a and b are equal, then there exists at least one point P on the curve between A and B such that the tangent at P is parallel to x axis. So the geometrical meaning can be understood by the following figure. Here you are having, if you see this diagram, in this diagram, this is x-axis, this is y-axis, this is the curve y is equal to f of x, okay, which is a continuous curve. Then at this point A and at this point B, you'll be having the ordinates A and B. So between this A and B, there exists at least one point P between A and B such that f dash of x is equal to 0. That becomes a tangent line parallel to x-axis, at this point. Then if we are having more than one tangents, so say for example, this is another curve, this also is a continuous curve, this also is another continuous curve. Then in between these 2 points A and B, wherever having that f of A is equal to f of B, then in between this A and B, there exist the points P1 and P2 at which the tangents are parallel to x-axis. So this number may go on increasing. You may have any number of tangents for this curve which may be parallel at the points P1 and P2. So this becomes what you call the geometrical implication of the Rolle's theorem, or indirectly we have proved that between this A and B there exist the points P at which the tangent is parallel to x-axis. That means f dash of C is equal to 0 between A and B. Here also f dash of C1 is equal to 0 and f dash of C2 equal to 0 at these 2 points P1 and P2. Then we'll see what is the algebraic meaning of this Rolle's theorem. If A and B are two consecutive roots of a polynomial equation f of x is equal to 0, there exists at least one root of f dash of x is equal to 0 between A and B. So this is what we call the algebraic interpretation of the Rolle's theorem. So firstly we have seen the geometrical implication, then this is the algebraic interpretation. Then the third one, the physical interpretation, for example, where exactly you are applying this Rolle's theorem. Then the instantaneous rate of change of f at some point C between A and B is 0. Okay, so this may be applied when you go for finding either the velocities or the accelerations of the moving points at any instantaneous time. So therefore, this becomes the physical interpretation of the Rolle's theorem. Then we'll see some of the illustrations on Rolle's theorem. That is the examples on Rolle's theorem. The first one, test the application of Rolle's theorem for the following functions. The first question is f of x is equal to x squared in the closed interval -1, 1. The second question is f of x is equal to tan x in the closed interval 0, pi. And the third question is f of x is equal to x into bracket x plus 3 multiplied by e to the power minus x upon 2, where x belongs to minus the closed interval -3, 0. So we'll just see how this function f of x, whether it satisfies the Rolle's theorem or not. So we'll have to consider all that three conditions for these functions to verify the Rolle's theorem. What are the conditions? F of x must be continuous in the closed interval. F of x should have a definite derivative in the open interval, and f of a must be equal to f of b. If these three conditions are satisfied, then there exists at least one point C belonging to this open interval such that f dash of C is equal to 0. Okay, so that was what we call the Rolle's theorem. Then we'll see step by step how that three conditions are satisfied for these functions or not. The first one, here f of x is equal to x square, where x belongs to the closed interval minus 1, 1. So here f of x is equal to x square being an algebraic function. And we know that all the algebraic functions are continuous. And in particular, this f of x is equal to x squared is a continuous function in the closed interval minus 1, 1. Then also the derivative of this, that is f of x is a function of x. If I find the derivative of this f of x becomes f dash of x, and this f dash of x is equal to 2x, is a differentiable function in the open interval minus 1 to 1. And also we have to see that whether f of a is equal to f of b. Here a equal to minus 1 and b equal to 1. Therefore, f of minus 1 is equal to minus 1 square is equal to 1. And also f of 1, 1 becomes 1 square is equal to 1. So therefore, f of minus 1 is equal to f of 1. Therefore, all the conditions for this function f of x is equal to x square are satisfied, and hence by Rolle's theorem there must exist at least one point x is equal to c belonging to this open interval minus 1, 1 such that f dash of c must be equal to 0. So from the first derivative, we have f dash of x is equal to 0, implying thereby 2x is equal to 0, and hence 2 is not equal to 0, then x must be equal to 0, so that x is equal to 0. Therefore, f dash of c equal to 0 implies that 2c equal to 0, and hence c is equal to 0. Now, c is equal to 0 belongs to the open interval minus 1, 1. Rather, this is the origin. Here, this is minus 1 and this is plus 1. So, therefore, there exists at least one point c which is equal to 0 in this case, and hence all the conditions of Rolle's theorem are satisfied, and hence the Rolle's theorem is verified for the given function f of x is equal to x squared in the interval minus 1 and 1. So we'll see the next question, that is f of x is equal to tan x defined in the closed interval 0 pi. So first you will have to go for whether this function f of x is equal to tan x is a continuous function in the closed interval or not. So when we put that x is equal to 0 to pi, that x is equal to pi by 2. Now when you find the continuity, continuity has to be there for all the values of 0 less than or equal to x less than or equal to pi. So therefore, when x is equal to pi by 2, then automatically tan of x is equal to tan of pi by 2. And tan of pi by 2 is tan 90 degrees. That is sine 90 upon cos 90. Sine 90 is equal to 1, cos 90 is equal to 0. Therefore, 1 upon 0 is equal to infinity. Therefore, this when x is equal to pi by 2, this becomes infinite. Hence, the function f of x is discontinuous at the point x is equal to pi by 2. Hence, the first condition of Rolle's theorem is not satisfied. And also, if you see that f dash of x is equal to that second square x exists in the open interval 0 and pi. Also, that f of 0 is equal to tan of 0 is equal to 0, and f of pi equal to tan of pi is also equal to 0. These two are also equal to 0. Therefore, f of 0 is equal to f of pi. So, the two conditions may be satisfied, but the first condition is not satisfied. Therefore, you cannot say that the Rolle's theorem for f of x is equal to tan x is satisfied for this function f of x is equal to tan x between the closed interval 0 and 5. Hence, that Rolle's theorem cannot be applied for the second function f of x is equal to tan x. Then we'll see the third function. Here, f of x is equal to x into bracket x plus 3 e to the power minus x upon 2, where x belongs to minus 3, 0. So again, if you see this question, here you are having this is x, x plus 3. Now, x and x plus 3, they together form an algebraic function. And e to the power minus x by 2 becomes an exponential function. Since x into x plus 3 being a polynomial function is a continuous for all the values of x between minus 3 and 0. Also, the exponential function e to the power minus x by 2 is also continuous for all x. In particular, the product function f of x is equal to x into bracket x plus 3 e to the power minus x by 2 is a continuous function in minus 3, 0. Also, the second condition, if we see that f of x is equal to this value is differentiable. That is, when you go for the derivative of this, the derivative of this becomes this is x square plus 3x. X square derivative is 2x plus 3x derivative is 3. Here this becomes a product function. Therefore, you will have to apply the product rule. So I got the derivative of x square plus 3x, which is equal to 2x plus 3. Then e to the power minus 6 upon 2 as it is. Then plus this x square plus 3x as it is. This value as it is. Then the derivative of this. The derivative of e to the power minus x by 2 is e to the power minus x by 2. And the derivative of minus x by 2 is minus 1 by 2. So therefore, when you simplify this value, this becomes 2x plus 3 e to the power minus x by 2 minus 1 by 2 x square plus 3x e to the power minus x by 2 is a differentiable function in the open interval minus 3, 0. Then also, if you see this f of 0 is equal to f of minus 3 is equal to 0. F of 0 is equal to 0. F of minus 3 is also equal to 0. So here you are having this f of x is equal to x into bracket x plus 3 e to the power minus x by 2. So when x is equal to 0, this entire thing is equal to 0. So therefore, f of 0 is equal to 0. When you put x is equal to minus 3, this becomes x plus 3 minus 3. So this is minus 3, this is plus 3, this becomes 0. 0 multiplies to the entire value. So therefore again, this becomes 0. Hence, all the three conditions of Rolle's theorem are verified. Hence, there exists at least one point in the open interval minus 3, 0 such that f dash of x is equal to 0. So, the f dash of x is equal to e to the power minus x by 2, then into bracket 6 plus x minus x square upon 2. So, when you simplify this, the above derivative, when you simplify this value, the simplification of this is equal to f dash of x is equal to 6 plus x minus x squared by 2. Then when this is equal to 0, then what happens? E to the power minus x by 2 equal to 0, or this term is equal to 0. Then this term cannot be equal to 0 because this is an exponential function. So the exponential function is not equal to 0 for any value of x. Then this must be equal to 0. That is 6 plus x minus x squared by 2 must be equal to 0. Then 2 is not equal to 0. 2 will go on this side. Then this 2 is not equal to 0. Then this term must be equal to 0. That is 6 plus x minus x squared is equal to 0. Now this implies, take that minus sign outside and then cancel that throughout. This becomes x square minus x minus 6 is equal to 0. Now go for the factors of this. The factors of this are x minus 3 into bracket x plus 2 is equal to 0. This is x into x is x squared. Then minus 3x plus 2x is minus x. Minus 3 into plus 2 equal to 0. So therefore that becomes equal to minus 6 and this is equal to 0, implying thereby the product is equal to 0. So x minus 3 equal to 0 or x plus 2 equal to 0. When x minus 3 equal to 0 or x plus 2 equal to 0, so x minus 3 equal to 0 implies x is equal to 3 or x is equal to minus 2. Now out of these two roots, you are having that f dash of c equal to 0 implies that c is equal to minus 2, which belongs to minus 3 0. So x is equal to 3 does not belong. So therefore there exists at least one point c is equal to minus 2, which belongs to minus 3 0, and hence the Rolle's theorem is verified. So these are the illustrations on the Rolle's theorem. So in the next lecture, we will be studying other parts of Lagrange's mean value theorem and the illustrations on that Lagrange's theorem and so on and so forth. So for the time being, I wish you all the best and happy learning. Thank you.